Now, besides wanting to describe the positions of particles as a function of time, in physics we're interested in other kinds of things like waves. So in order to describe waves of different kinds, for example, waves traveling or ripples traveling on the surface of the ocean, or waves set up on a string, for example, of a guitar, or if we're talking about things like light waves, which are electromagnetic waves, we might want to be able to describe these things in some way. And the way we do that is, let's take a particular example. Let's take the case of electric fields. Let's take electric fields. So the electric field is described by a vector, E, where at each point in space I assign a vector. Okay, and this vector is the vector of the electric field. So the direction of this electric field tells me which direction the electric field is pointing at that particular position in space. And its magnitude tells me the amount of electric field, that is how strongly charges will feel the influence of this particular electric field. So the thing to remember is that this length has nothing to do with length in physical space, that is, it's not a length between two positions in space, but rather it's the magnitude or the strength of the electric field, which I'm just representing in a drawing over here by showing a length in space. Okay. Now you imagine that at every point in space I have an electric field, so there is a vector that describes the amount, the direction, as well as the magnitude of the electric field at each point in space. So this is at the point 1, this is at the point 2, this is the electric field 2, this is at point 3, there's electric field 3. And these could have differing lengths. Which means that they have different magnitudes at each position, and they have different directions at each position. So how do we describe an electric field? Well, again, we still need to set up our spatial locations because we need to describe what the electric field is at a particular location in space. And the other thing is, these electric fields could be changing as a function of time. They could be responding to the motion of charges. Okay, so if I have a charge, so we know that if you have a single point charge, this can create an electric field around it if it's at rest. And if it's in motion, it can also create magnetic fields. So if this charge moves, the electric fields move along with it, and it also creates magnetic fields. So we need to be able to describe the electric fields everywhere in space and at all instants in time. So in other words, we need to be able to talk about things like what is the electric field at a spatial position x at a time t. Okay, so once again, we need to be able to define a spatial coordinate, and we need to be able to define a time coordinate, which again requires that we define an origin, a set of axes, and a reference length to measure positions. And to measure time, we need to define an origin and a reference time interval. To measure electric fields, we would also need a reference electric field. Okay, and we're assuming that the coordinate directions with which we describe the electric field will be the same as the coordinate directions with which we measure our positions. All right, so whether we're describing the positions of particles as a function of time, or whether we're describing electric fields or ripples of a water wave, we need to be able to set up some way to describe positions and times. Okay. So now in this way of looking at the universe, we need to describe positions and times. So for particles, we need to describe how their positions are changing as a function of time. For fields, we need to describe how, for example, the electric field is changing as a function of different spatial coordinates and different times. Okay, so this kind of field is called a vector field. Okay, and you need three numbers to describe the electric field at every position. You need to be able to describe the x component of the electric field, the y component, and the z component. But you can also have what are called scalar fields, that is, fields like the electric potential, which is a single number at each point in space and time. So this is called a scalar field. And if we want to describe all kinds of interesting dynamical processes involving particles and fields, we need some kind of dynamical equations. And these dynamical equations tell us how quantities like x of t change with time. That is, how does this function x of the position of a particle change with time? And how does the electric field change as a function of both spatial position and time? Okay. Now, just to be clear about the distinction, the electric field is described at all positions and at a particular instant of time. This position here describes specifically the position vector of a particular particle. So this vector x is not the same as this vector x. This is a general position of a particle. So we could have just as well denoted it with some other symbol. For example, we could have used the symbol no, that's not a good one. We could have used the symbol y to denote the position of the particle. Okay, so this symbol here refers to the position of a particular particle that we're talking about. So let's say particle 1. Okay, whereas this coordinate describes all positions in space. So for every position x, I need to be able to write down what the electric field is at every possible time, all possible times. Okay, and for a particle, I need to be able to specify where it is at all possible times. Okay, so what we need are dynamical equations which tell us how quantities like x or y change as a function of time. The position of particle, how does it change as a function of time? And how does the electric field change as a function of both space and time? So for particles, they obey Newton's laws. And Newton's laws tell us that if there's a force acting on the particle, this force will produce an acceleration. So this is Newton's second law. Force is mass times acceleration. And the acceleration is the second derivative, or the rate of change of the particle's position as a function of time. Where this derivative is taken at some instant of time t. Okay, so what this does is it tells us how the second derivative of x of t, that is how this vector x of t, it describes the rate of change of this vector. Okay, and the rate of change depends on the forces applied to a particular particle. So given an initial position, so supposing we know the position of the particle at some time t naught, and suppose we know the velocity, that is the rate of change of position at some time t naught, And suppose we know the forces acting on the particle, that is, we know how this force and how it acts on the particle. We can solve this equation. It's a second order differential equation. We can solve this equation to figure out how the particle moves as a function of time. So given some initial conditions, and given the forces acting on the particle, you can figure out the trajectory. That is, what the particle will do in the future, okay, under the action of those forces. So this is what we mean by dynamics. We can figure out the motion of particles under the influence of its interactions with its environment. Similarly, for electromagnetic fields, we have Maxwell's equations that tell us their dynamics. So I'll just write down Maxwell's equations. So the first one is about the divergence of the electric field is related to the charge density at a particular location. So this is the divergence of the electric field at a particular location x and t, and this is the charge density at that location x and at the same time t. So the second equation tells us that the curl of the electric field is related to minus the rate of change of the magnetic field with time. Okay, this is called Lenz's law. So this is Coulomb's law. The divergence of the magnetic field at any location is zero. This is simply because, in analogy with the electric field equation, charges source electric fields, but there are no, as far as we know, there are no magnetic monopoles in nature. So this is telling us that there are no magnetic monopoles. And lastly, the curl of the magnetic field is equal to the rate of change of electric field with time multiplied by epsilon naught plus mu naught times J. This is Faraday's law. Okay, so you have four equations. Well, in reality, this is slightly more than four equations because this is a scalar equation. The quantity on the left is a scalar, so this is one equation. This is three equations since it's a vector equation. This is again a scalar equation, so this is one equation. And this is three equations, again, since it's a vector equation. So the total number of equations that we have, Maxwell's equations, is 3, 4, 7, 8. 8 equations. And these equations describe how the electric fields and magnetic fields change at different times. So they describe the dynamics of the electric field. For example, if you don't have any charges or current densities, then you can show that you can combine these Maxwell's equations to get a wave equation. So you can show something like this. Okay, in the absence of charges and current densities, you can get an equation of this form. So this is a wave equation. And of course, we know that light is a traveling electromagnetic wave. Okay, so you can solve this kind of equation to figure out how electric fields change as a function of position and time.